So, hi everyone, welcome to this new meeting of the 40 under 40 lecture series on combustion. It's the first after the summer, and it is my great pleasure to introduce Professor Noud Maes. He's an assistant professor at the mechanical engineering at the Eindhoven University of Technology. He's jointly responsible for the zero emission laboratory that hosts several experimental setups. And the focus here is really the ultra clean engines and the fuels of the future. Now, his expertise is actually in high pressure jets and sprays, in internal combustion engines, fuel technology, combustion and high speed diagnostics, as well as laser measurement techniques. His PhD comes from TU Eindhoven in 2019, where he was focusing on high pressure fuel sprays, and he was also a researcher at the French Institute of Petroleum and at the Combustion Research Facility at Sandia National Laboratories, where he had guest periods. In 2019, he started a postdoc position at the CRF, and then since 2020, he's holding this current position at TU Eindhoven. So today, we talk about internal combustion engine research activities at the Zero Emission Laboratory in TU Eindhoven. And it's really my pleasure to have you here with us, and I give you the word for your talk. Thanks again.
All right, thanks a lot for the nice introduction. Yeah, so the topic for today will be some of the things that we do in our zero emission laboratory. I will talk a little bit about the vision and the organization of our lab. Then I will introduce at least several of the setups that we have. And then I will switch gears and talk about some of the recent and the current work that we have done with these setups in our lab. I think it is relatively clear for most of us what our goal is here. So in our zero emission lab, we have the vision that aligns with the EU-funded Mission D+, which is emission-free, future-proof mobility for people and goods by 2050. And that is associated with several targets, among which are, zero-emission public transport, but also zero-emission zones in larger cities. And that goes hand in hand with the introduction of electric vehicles, of course, but also renewability of energy in mobility. And associated with that, specifically for heavy duty transport, we need to look at sustainable fuels in order to achieve those. In our lab, we have something that we coin ICE 0.0. That means internal combustion engines 0.0, where we focus both on zero impact greenhouse gas emissions as well as zero impact pollutant emissions. Well, for the greenhouse gas emissions, of course, you have to look at the fuel side. You want to avoid fossil carbon here. That's the thing that you want to avoid in order to have the zero impact greenhouse gas emissions. And that means that we look at either hydrogen and ammonia as a carbon-free fuel, or we look at advanced biofuels and advanced electrofuels, fuels generated by renewable electricity, in order to do so from the fuel perspective. On the other side of the coin, we have the zero impact pollutant emissions. That's partially related, of course, to the fuel again, but also largely based on the engine that you're using. And that means, of course, that we're targeting zero impact NOx, soot, unburned hydrocarbons, and CO emissions. Well, we believe that the way to do this is to use this combination of ultra-efficient internal combustion engines and sustainable fuels. So we have to combine these two things to accelerate the greenhouse gas emission reduction in heavy-duty transport. And some of the key scientific challenges associated with this are the formation of mixtures inside the cylinder, but also to shape the heat release inside the engine and to control this heat release as a function of time. In addition to that, we also believe that we need to have certain fuel flexibility in order to meet up with the specific supply and demand. Well, the way we do that in our zero emission laboratory, this is an initiative which is joined by the university, so TUE. We also, in our board and program advisory committee, have TNO, which is a Dutch research institute. We have DAF, the local truck manufacturer, situated in Eindhoven as well. And then in our board and program advisory committee, we also have chairs for people from Shell. Well, we do three different things in our lab, in our initiative, so to say. That is concept studies on engines. We have advanced, typically optical experiments on combustion. And then we also have advanced numerical simulations for the projects that we do, meaning that most of the research that we do is based on both the combination of experiments and numerical simulations and the comparison of those. I will not focus on this part of the research in our initiative today, but rather I will talk about some concept studies and some optical experiments on combustion today. Here are also some people that are associated with the research that we have in our lab. And of course, in addition to that, we have indispensable help from many support staff members, as well as students and PhD students, some of which will also be listed specifically today. To kick off, I have a little bit of an introduction movie about our Zell. So make sure that, I think you should have your sound on because otherwise you would not hear me. So I will play a short movie that has sound included as well. It's a 1 minute movie of our lab.
The pursuit of a sustainable future. It's a journey on a road we discover along the way. No clear destination, no beaten track to follow, and hardly any time left on the clock. All we know for sure now is we simply cannot make it without internal combustion engines. Especially in heavy transport, these engines are indispensable. Here, in the Zero Emission Lab, we explore, we test, and we log our journey. Our research focuses on green fuels and clean engines. More efficient, less emission. Simple as that. Yet one of the biggest challenges of our time. Let's dive deep into the most fundamental problems we can find. Care to join us?
All right, so as already mentioned, we host several experimental setups in our lab. I'm showing most of them on this graph, where on the y-axis we see how close they are to the real-world application, meaning very applied, an actual engine. And on the x-axis we see the fundamental nature of the research, meaning that here on the bottom right we simply have combustion at quasi-steady conditions to study different fuels. I'm also highlighting in blue the setups that we use for ultra clean engine concepts, looking at different combustion concepts, while in green I'm targeting the setups that allow us to really study different types of fuels. And of course, in many cases, especially here in the middle, we can combine those two properties for the setups that we have. I truly believe that some of these setups are unique even on a global scale, and that leads to a lot of unprecedented research capabilities in our lab. I will talk about, or at least introduce, a couple of these setups before going into some of the results that we have obtained in the past years in our lab. So to start off with, we have several setups that allow us to analyze the lubricity, the stability, but also the elemental composition of our fuels prior to testing these fuels in our engines. And that's because, well, first we want to use, or we want to understand whether these fuels can be used, whether they are applicable and usable in our engines. We want to prevent damage to our other setups. And also we have to realize that some of the fuels that we are testing have limited batch sizes, specifically for the biofuels and the e-fuels that we test. Then we have several HOTS engines. These are single cylinder diesel generator engines. They are equipped with emission and in-cylinder pressure analysis to study combustion. They are relatively robust, cheap, and fuel flexible in our case for direct injection compression ignition engines. And we even have 3 of these that are placed on moving frames that we use in our courses for bachelor students, where they can test different fuels and then analyze how, let's say, sustainable these fuels are, and they have to write reports about that. A bit more sophisticated is our PACCAR MX-13 single-cylinder reactivity controlled compression ignition capable engine that's shown in the picture here on the top right. This is a modified single cylinder engine that allows us to study different combustion concepts, where here on the left hand side we see the classical flamethrowers caused by classical diesel combustion, while on the right hand side we make use of two different fuels, one low octane, one high octane fuel, in order to perform reactivity controlled compression ignition. The idea here is that we try to achieve low emissions with combustion phasing control. So we have our high octane fuel injected in the intake. We have our low octane fuel, so more reactive fuel, injected directly into the engine. And the ratio between this, as well as the timing of the direct injected low octane fuel, allows us to facilitate combustion at the right moment in time without having direct coupling between the moment of injection and ignition of that fuel, the compression ignition. In terms of soot emissions on the y-axis and NOx emissions on the x-axis, that means that this typical trade-off that we see for classical diesel combustion, where we either have high soot or high NOx emissions, is really broken, and we arrive at this near zero soot and NOx emission area for RCCI type of combustion. Then we have several optical constant volume vessels in our lab. The most sophisticated one is the Eindhoven high pressure cell, or abbreviated as EHPC. In this constant volume vessel, which has a volume of about 1.3 liter with 100 millimeter optical axis windows, we fill this setup with 4 different gases: acetylene, argon, nitrogen, and oxygen in a sequential fill. And then we ignite this charge, leading to a pre-burn and a quick rise in temperature and pressure, as shown in this graph here, which then gradually comes down over time. So there's a relatively long cool down period. And when we cross the conditions in which we are interested in for our let's say our engine type conditions, we inject our fuel, and we can then study that with the optical axis. We can arrive at densities up to 40 kilogram per cubic meter, pressures of 350 bar, temperatures of 2000 Kelvin, and based on the amount of oxygen that we fill during this pre-burn, we can arrive at 0 to 35% oxygen after the pre-burn, in which we inject our fuel. And that means that we can study inert vaporizing conditions, or conditions where we do have oxygen for combustion, let's say oxygen enriched conditions, if you wish. Well, that allows us to visualize the vapor phase fuel, the liquid phase fuel, but also species distributions using laser-based diagnostic techniques, as well as chemiluminescence, for instance, or we can also study soot in the case of carbonaceous fuels. We have a smaller constant volume vessel with limited optical axis. That is a combustion research unit, which is a commercial ignition quality tester. This one has a volume of about 0.4 liter, and here the conditions are reached by preheating compressed gas that is admitted to the chamber. In this case, we can arrive at engine-like conditions of pressures up to 60 bar, peak temperatures up to a little over 1000 Kelvin, and oxygen percentages again between 0 and, in this case, 21% oxygen. This is a robust and fuel flexible commercial setup for analyzing mostly the heat release that is caused by the injection of our reactive fuel, and there's a limited optical access point through a borescope from the bottom of this small vessel. It is also equipped with a dual circuit heavy fuel oil injector that allows us to study very viscous fuels that are more applicable to, for instance, marine applications. Then we have our Eindhoven low pressure cell. This is a small version of the vessel introduced earlier. In this case, the volume is 1 liter. And in this case, we do not have a pre-burn, but instead we fill the vessel simply with compressed gases, which can be nitrogen, helium, argon, or mixtures with oxygen, of course. The pressures can go up to 50 bar, but this is all at room temperature. And so far, we've mostly used this for hydrogen research with a fuel pressure up to 100 bar, where we still have full optical axis, and we can study, for instance, the Mach disk formation of hydrogen jets, but we can also do mixing and penetration studies at room temperatures. Then one of the final setups that I would like to introduce is our momentum exchange setup. In this case, this is a small force sensor with a plate mounted in front of it. And that allows us to study the force that is generated by an injector. That can be a liquid or a gaseous injector that's injecting onto this plate, and then we measure the force introduced by that injection, and that allows us to determine essential parameters for modeling fuel injections. In combination with a syringe pump, we can do that for liquid fuels, and also simultaneously inquire the mass flow of the injector up to pressures of 2000 bar, 200 MPa. But currently we've been using this a lot for hydrogen injections, where we can use up to 200 bar gas bottles to study the momentum generated by a hydrogen injector. And then the final setup that I would like to introduce is one of our optical engines. This is our engine that we're currently converting to hydrogen operation as well. In the base, this is a single-cylinder 2-liter compression ignition engine based on the Proteus Recaro base. We've equipped this with a DAF MX-13 liner, piston, and engine head. And this engine makes use of an extended piston, a bow ditch design that's shown schematically over here. That means that this piston moves up and down with a cutout from the side where we can place a 45-degree mirror in this piston itself, and that allows us to look from the side into the engine from the bottom. So from the side we can move through this this hole, and then we have this 45-degree mirror that allows us to look upwards into the combustion chamber on the top. We use quartz and sapphire pistons in this engine to facilitate the optical axis. We can adjust the compression ratio, and what we use here is flexible skip firing, and I will come to that later on as well when introducing some of the work on this engine. So some of the current and recent projects that I will highlight today is the Smart CHP Combined Heat and Power project by Dr. Wang, who defended his PhD last year in May. His PhD project was on the use of fast pyrolysis bio-oils in engine. I will have a couple of slides on the Argon power cycle, where Dr. Max Peters defended this year in May some of his optical studies on hydrogen jets in nitrogen and argon environments. Some of the work by Dr. Wang will also be included, who did a postdoc within this project after his PhD. Then I will talk a little bit about future fuels studied by our Chinese Scholarship Council student, Dr. Sun, who defended last week, in fact. So that's on biofuels and oxymethylene ethers, OME fuels. And then finally, two more hydrogen projects. First of all, the rebuilding of our optical engine for hydrogen use by Stan Latte, and a hydrogen pre-chamber study by Noud Maes in the high use project. So Smart Combined Heat and Power by Dr. Wang. The idea here is that we use different types of non-food biomass, particularly residues. We convert these in pyrolysis oils in these pyrolysis plants. And then the idea is to use this in a smart combined heat and power system, where part of it is directed towards the flue gas boiler. But our focus in this project was to look at the use of FPBO, fast pyrolysis bio-oils, in a modified diesel engine. The technical goals for this project was to have a small scale unit between 100 and 1000 kilowatt electric in terms of power. The heat to power ratio should be flexible between 1:1 and 10:1, so more heat compared to power. The overall combined heat and power efficiency should be beyond 85%, and then the greenhouse gas emission reduction compared to fossil fuels should be above 80%. Well, some of the applications or future users are listed here, so that can be industry, remote areas, service sectors, or district heating. But of course, the challenge here is that, well, FPBO is, when compared to diesel, rather viscous, times 15 the viscosity. It has a relatively low energy density, partially because of the high oxygen and water content. It may have some impurities in terms of particles, and it is also strongly acidic. That means that in engine applications, well, we didn't know how the ignition properties would be and the combustion characteristics, but also we had to take care of the corrosivity, the nozzle clogging, and the poor ignitability relating to this first point. The idea was to study this in a three-way approach. First of all, we used one of our constant volume combustion vessels in this study. We also did some modeling, looking at a two-stage Lagrangian model. And then we did our engine testing to look at durability, the emissions, and the efficiency of the fuel in this engine. First of all, we tested this in our constant volume vessel, looking at the natural luminosity of diesel and FPBO. We quickly realized that after 13 injections, already our nozzles were clogging. That is visible here. And after 16 injections, even more of the holes in our injectors were clogged, meaning that we really could not even inject fuel anymore at some point. That's also shown here with the heat release as a function of time. So you can clearly see that over time, the heat release comes down. And in addition to that, we can also see that compared to the dashed dotted line of diesel, we have a longer ignition delay when it comes to the injection of our FPBO. But definitely, we can only do a couple of injections before the injectors clog in this case. Well, in order to improve this behavior, we had to increase the injection pressure from 300 to 900 bar. That already improved the nozzle durability a lot. It also improved the atomization, but particularly when we added ethanol in terms of 30% ethanol with FPBO, we further improved the atomization, we reduced the sooting tendency even more, and we also slightly managed to shorten the ignition delay of our fuel. We tried to understand this further using a two-stage Lagrangian model that was specifically built by U to simulate spray combustion. So this is a minimalistic flow model, a 1D entrainment model with two different reactors, perfectly stirred reactors with transport between them. And then we could use detailed chemistry to resolve combustion. With this model, we were capable of showing that we could show how eventually our fuels had a multi-step ignition process with transport between the spray core and the periphery regions. We validated this model using well-known conditions from the engine combustion networks, so-called spray A conditions. And the conclusion was this is a very powerful tool to investigate spray ignition processes. We then applied it also to FPBO and blends with ethanol, and we saw that we needed rather high temperatures for the ignition of our FPBO ethanol blends, but that ethanol specifically promotes the second stage ignition of our fuel. Then finally, Dr. Wang also did dedicated engine modifications to run an engine on FPBO. We had to intake heat the engine and elevate the compression ratio. We implemented a fuel switching dual circuit injection system to make sure that there is no contact of the FPBO with some parts of the injector. And then doing these modifications, these are schematically shown here on the right-hand side. For the first time ever in the world, we managed to do unattended operation of 500 hours durability on an engine with pure FPBO. So that was great success. We also showed that the efficiencies and the emissions were actually better than operating the same engine on diesel. We improved the thermal efficiency, net indicated efficiency, because of the faster burning rate at these conditions with FPBO. We also managed to show that we had lower NOx emissions, again, probably because of this addition of water to the fuel, but we did show that we had slightly higher CO emissions compared to diesel operation. Then I want to switch gear and talk a little bit about the Argon power cycle, which was worked by our former PhD student, Dr. Peters. The traditional situation is shown here. So we have an engine that runs on air, so oxygen and nitrogen, and then we inject our fuel, and then we have our exhaust gases with compression ignition. But the idea here is that instead of air, we use argon, and we use this in a closed loop. And the idea of using argon instead of air with nitrogen is that our theoretical efficiency gets a boost from maximum of 55% to about 80%. And that's based on the thermodynamic efficiency shown here. And the reason of using argon is that because of the fact that this is the cheapest monatomic non-toxic gas, and ideally we recirculate this then so that we do not have to provide constant flow of argon to an engine and losing that to the environment. Well, of course, the way to do that is by using hydrogen as a fuel, because if we then have hydrogen and oxygen reaction, we form water. Well, we can condense that, and that makes it easy to separate from the argon so that you can recirculate the argon in the engine. And that'll also allow us to operate free of NOx emissions because, well, there is no nitrogen. That means that the Argon power cycle enables pollution-free power production and very cost-effective hydrogen energy storage and utilization on site. Well, we first characterized injectors. For this work, we used Bosch HTEF 1.x injectors. We used several different versions where we had orifice diameters ranging between 0.55 millimeter and 0.65 millimeter, and we modified the lift of the needle and the swirling plates inside these injectors. With the traditional injector, we noticed that we did a modification of the injector to open it up on the sides to visualize with optical techniques the injector needle itself, and we managed to visualize that this needle would have a lift of about 75 micron. We then validated this using laser Doppler vibrometry in our lab as well, where we used or removed the back part of these injectors, placed a small reservoir with an optical window there, and that allowed us to study the lift on the back side of the needle while operating the injector with fuel. And there we confirmed this lift of between 73 and 88 micron while operating at different fuel pressures. We also did CT scans of the injector, noticing that the smallest area for the gas to pass was around the needle lift area over here in the injector. So that's all the way here in the front as well. We did mass flow measurements in a dedicated, very small constant volume vessel that I did not introduce before, where we also installed thermocouple measurements to correct for the temperature increase of the injection, to characterize the amount of mass being injected with every hydrogen injection. And then finally, the setup that I did introduce, the momentum flow measurement, where we did 4 sensor measurements to characterize the momentum generated by these injectors. Here are some of the conclusions. I won't go into a lot of detail here, but what we notice is that there is a significant loss of the flow coefficients inside the injector. So the discharge coefficient, that's this column over here, shows that for our prototype injector that we had initially, we would lose, let's say, half of the energy, more or less. But we also noticed that if we remove the swirler plates inside these injectors, or if we increased the needle lift, then we would be able to reach higher discharge coefficient values, increasing the mass flow of the injectors. Well, we then studied the jet penetration of these hydrogen injectors in our smaller low temperature pressure vessel. And what we confirmed is that based on jet theory, we know that the jet penetration is really a function of the so-called nozzle pressure ratio, which is the fuel pressure divided by the ambient pressure. And that is shown here in the jet penetration as a function of time graph, where you can see that if you have different injection pressures, these 3 lines, they overlap here. They have different injection pressures, but the nozzle pressure ratio is approximately the same, about 4 in this case. And therefore, with different injection pressures, you still get the exact same jet behavior because the nozzle pressure ratio is the same. What does change the situation if you move from nitrogen ambient to an argon ambient, because then you notice that the jets move much slower, but you still have the same discharge coefficient and the same mass flow. And that is, of course, caused by the difference in density. So if you then correct for the density between argon and nitrogen, you get a ratio of about 1.4. Then you get very similar jet behavior again. We also did quantitative mixing studies. For this, we used Rayleigh scattering for gas jets. The equation simplified of the total relationship for Rayleigh scattering is shown here. The idea here is that you get both intensities of the jet as well as the ambient in a single shot, and that's shown here with a color camera, DSLR camera here on the right hand side. You have your laser entering the vessel from the left-hand side, so you have the Rayleigh signal in the ambient, and then you have the Rayleigh signal in the jet itself. The bad news is that Rayleigh scattering for a hydrogen jet means that the Rayleigh cross-section of nitrogen or argon and hydrogen is very close to one another, and that means that your signal-to-noise ratio, especially when you compare that to, for instance, N-heptane gas, yeah, your signal-to-noise ratio is very low, and that means that you really have to optimize your optical system using a backlit CCD camera, a fast lens, and yeah, let's say well-chosen filters for both the light as well as for the particles inside the setup. One of the assumptions that you need in order to get to this relationship is the number density of the ambient as well as the number density in the mixture. And the assumption here is that these are equal. And we validated this by performing argon into argon injections. So we injected argon from our injector into a vessel filled with argon, because then the Rayleigh cross sections are identical, and that means that you get a direct measure of this number density, and that shows that indeed outside of the Mach disk, and this Mach disk area is only a couple of millimeters in terms of nozzle pressure ratio that is representative for engine operation. And that shows that there is signal close to the nozzle inside the barrel-shaped shock, but outside of that, yeah, the number density equal to 1 assumption holds, and that allows us to do quantitative Rayleigh scattering measurements in our jets. Well, then you get results like these. Here you see the initial results of Rayleigh scattering, and then if we do a 1D row interpolation to correct for the beam steering inside the jet itself, we get images like this one on the right-hand side. Well, here are some quantitative results. This is showing the mole fraction in the color scale between 0% in the ambient and then 1 all the way here at the tip of the injector. And this is the standard deviation of multiple injections here, while the different rows here show different timings after the start of injection. We also did a second study where we wanted to quantify mixing of hydrogen using inverse laser-induced fluorescence using an ambient tracer. So we seed the ambient of a vessel with a tracer. In this case, we used both toluene as well as acetone to then study the LIF signal and the mixing with the jet. This was a collaboration with IFP in France, where we collaborated with Michele Bardi and Hugo Quintens at IFP. For toluene, we had to use an intensified camera because it was using UV. Well, toluene results in LIF signal in the UV range, while for acetone, we could use our backlight illuminated CCD camera again. And we eventually chose this setup because it enhanced our contrast a lot, and that also resulted in much more accurate mole fractions using this equation here on the right in the center of the screen. We then compared our acetone results to Rayleigh signal that I was introducing on the previous slide. So each time in these panels, which correspond to different injection timings, or sorry, different times after the start of injection. On the top, we each time see the mole fraction measured by acetone LIF, and then on the bottom, we see the corresponding Rayleigh signal. We find 5 to 10% higher mole fractions for Rayleigh, and we also see that there is a reduced impact of laser attenuation and multiple scattering in our Rayleigh results. And that's also shown here in these, in these quantitative centerline plots where we see the signal as a function of axial distance from the nozzle, where we see that again, Rayleigh is always a little bit higher than the LIF signal. We did another additional absorption correction, which reduced the difference slightly, but we never got to the same values as we got with Rayleigh scattering. And finally, we also did hydrogen combustion experiments in our Eindhoven high pressure cell. I will not go over that slide, but I will show a couple of nice movies if they run. See if that works. Okay, that may not work. Oh. Okay, for some reason my presentation
all good
to run. Yeah, I'm still audible, I guess.
yes You are.
But I guess the movies that I was trying to show are
Okay.
relatively. Let me try that again.
Yes.
That works.
Go ahead.
Otherwise, I will skip this slide. Switch this one. I still have to reshare my screen. Go. Share. Okay. I guess I should be visible again. Perhaps you can confirm whether the slide is now running again. I don't hear anything.
I see the video. Yes.
All right, perfect. All right, thanks for confirming. All right, so we did hydrogen combustion experiments in our constant volume vessel. Here on the top right, we see a true color image. Here we see high-speed chemiluminescence, and then on the bottom we see Schlieren measurements that we've done to visualize the differences in refractive index caused by differences in density in our injections. So we did these simultaneously to really study these hydrogen injections in great detail. By this, we created a large database of hydrogen injections into different atmospheres, so containing nitrogen or argon with or without oxygen. We studied different ambient temperatures ranging from 900 to 1400 Kelvin. We did different oxygen percentages ranging between 0 and 21% oxygen. And then we used these different optical diagnostic techniques. And here I'm showing simply the correlation between the ignition delay measured based on the pressure measurements, as well as based on the chemiluminescence measurements. In order to analyze the pressure inside the vessel itself, we had to do several corrections. So what I'm showing here in blue is the pressure as a function of time during this cool down of the vessel itself. And then we get a small pressure increase because of the injection of hydrogen in a 0% oxygen case here. And then it cools further. Well, we then can correct for heat loss. That's the orange line here. That's a heat loss correction. The green is the result of correcting for heat loss. Then the orange is when we also correct for the amount of moles that we inject. In purple, we have a correction for the cold air, or the cold hydrogen that we correct. So we correct for the enthalpy. And then if we combine all of these, we get the light blue line, meaning that, of course, if we do all these corrections, we should be pretty close to 0 kPa pressure increase. But as we can see, this depends a little bit on the different ambient temperatures. That's the difference here on the top. But overall, we are rather satisfied with the with the corrections and the resulting close to 0 pressure increase when we inject our fuel. Well, then we move to a pressure increase when we do have oxygen and therefore combustion. Here on the y-axis, I show the total pressure increase as a function of the ratio of specific heats. And that ratio of specific heats is, of course, coming from the difference in oxygen percentage in the vessel. So here, when we move along with this green arrow, we decrease the amount of oxygen inside the vessel itself. And therefore, we increase the ratio of specific heats and we increase the total pressure increase caused by combustion because, that's the theoretical relationship that I showed before. The different points here then furthermore correspond also to different ambient temperatures. So what we first see, if we increase the ratio of specific heats inside our gas with hydrogen combustion, then we can get a up to 65% pressure increase. But of course, the amount of energy released by the fuel is the same. It simply results in a higher pressure increase, which is usable for an engine, of course. And what we also see is that we need at least, now the different colors represent the different ambient temperatures, we need at least a temperature of 1100 Kelvin to properly ignite or to have complete combustion of our hydrogen inside this vessel. Meaning that these cases with 1000 Kelvin, they only show partial heat release and incomplete combustion. The maximum pressure is arrived at this 1100 Kelvin, and that's because, well, the ignition delay for these cases is the longest, and that means there is the more premixed burn and therefore less heat losses for these cases. Then finally, in one of our HOTS engines, we also did closed loop Argon engine motoring. So we had Argon connected to our engine, and then we had a closed loop where we recirculated this Argon in our engine, but we did not inject any fuel. And using this with some losses, some gas losses from the engine itself, we were capable of running the engine up to 97% Argon. Doing so, we can see that the motoring pressure inside the cylinder increases from about 45 to about 85 bar, and the ratio of specific heats increases from about 1.18 to 1.38 based on this Argon volume fraction again. And that means that we can estimate a temperature from that, and that nicely aligns with some of the results that we got from our combustion vessel, showing that the estimated top dead center temperature goes from 650 Kelvin to slightly above 1100 Kelvin when we reach Argon percentages of about 90%. So that's good news. All right, then I'll shift gears a little bit again, talking about the PhD project by Zhongcheng Sun, who studied a pathway to sustainable fuels, where he looked at both short-term and long-term solutions in our setups. He first studied some gas to liquid fuels as an, let's say, potential anything to liquid, so any power generated to liquid type of fuel for the future. He also looked at GTL blends with 30% of biofuel, so 30% volume of FAME, fatty acid methyl esters. And he looked at a potential e-fuel, which is oxidimethylene dimethyl ether, which has no carbon-carbon chains, and it has quite a bit of oxygen in between these carbon molecules, as you can see from this figure here on the in the center of the slide. Well, first of all, GTL and GTL B30 blends, so 30% biofuel, they are considered as a nice short-term drop-in fuel for diesel engines. And what he showed that if we implement these fuels, so here we see difference maps of GTL minus diesel in terms of NOx and GTL B30 minus diesel NOx emissions. He showed that if you simply replace diesel by GTL or GTL B30, then your NOx emissions in the in the first fuel, they drop by 16%, but for a GTL mixture with 30% biofuel, they may increase by 8.3%. Well, that's of course not a very fair comparison, because what we know is that based on the fuel composition, we typically need to optimize the engine. So we need to tailor the operation of the engine to the fuel that we're using. If you do that based on purely the amount of exhaust gas recirculation in our engine, then we notice that for GTL, we can get a reduction of about 41.9%, while for GTL B30, we can arrive at a reduction of 55.5% in terms of NOx emissions, while adhering to the Euro 6 soot limits based on the Euro 6 soot limits. And that's shown here. So for different operating points, so the numbers in this in these different y-axis values, they represent the load of the engine, meaning 30% load, 50% load, and 70% load, while the letters here, A, B, and C, correspond to different engine speeds. So this really shows that depending on the operating point of the engine, we need to increase or decrease the amount of EGR in the engine if we move from our diesel fuel to one of these more sustainable fuels with a lot of bio components. Another alternative for a slightly longer term solution would be OME. OME is a potential e-fuel, as mentioned before, which at the moment is relatively expensive. And this brought us to the idea that, well, if it's so expensive, do we actually need all of it? Or if we have a certain amount of this sustainable, renewable e-fuel, can we blend that with other fuels in order to gain some benefit? For this, we selected a case here on this soot versus NOx map, which is relatively polluting. That's B speed with 30% load. That produces the most soot and NOx emissions across the engine map when running on diesel. And that's the point that we chose to optimize. We then used a design of experiments approach to provide a comprehensive global emissions map. So here we varied injection timing, the amount of exhaust gas recirculation, and the amount of OME in our mixture with diesel in order to find an optimum in terms of emission and efficiencies. And that is shown here on this graph. I realize this is a very busy graph, but I'll try to explain it in a little bit of detail. So on the y-axis, we have the amount of OME in our diesel fuel in this case. So ranging from low amount of OME to a high amount of OME. On the x-axis, we have EGR, so just a little bit of exhaust gas recirculation on the left-hand side. And on the right-hand side, we have a lot of exhaust gas recirculation. And what we can then see in the different colors is here on the bottom, we have a lot of soot emissions, and that becomes less when we move in this direction, while NOx emissions decrease when we move from left to right. And then we also have the gross indicated efficiency in different colors. This is also the particle emissions that we measured. And then here in this color scale, we see the fuel consumption. What we can tell based on this comprehensive maps is that there is only a slight negative impact of NOx emissions by addition of OME, but this is of course significantly mitigated when we increase the amount of EGR. What we find based on this map is that if we run our engine on this B30 condition, then based on the Euro 5 NOx and Euro 6 PM emissions, we can get compliance with these emission limits without after treatment if we run on 24% OME and EGR percentages above 37.2%. But if we do include some after treatment system, which can be relatively simple compared to a real, the current diesel engines, even with only 12.5% OME, we can get a significant benefit, reducing the amount of after treatment systems significantly, with only a small addition of OME fuel to our diesel blends. We also studied some of this optically, and I will not go in a lot of detail here, but here I'll show the heat release as a function of time. But more importantly, here we see the natural luminosity caused by either diesel or increased fractions of OME. And what we see specifically is that, if you increase the amount of OME, the amount of natural luminosity that you detect in such a combustion system is much reduced. And that's because at some point you don't have any soot formation anymore at all, and you're purely looking at chemoluminescence. That's also showed and visualized in these high-speed movies from our high-speed or more sophisticated high-pressure vessel. On the left-hand side, we see a recording where we see the yellowish flame caused by soot luminescence, while on the right-hand side, we see this OME flame showing only blue light. And that is something that we've characterized in many different experiments, looking at the ignition delay at different points, the liftoff length, the OH star distribution. And there we try to really understand where this soot reduction potential of OME was coming from. And we linked that to much lower equivalence ratios in the flame, again substantiated by these simulations here, by a 1D model, and the lack of carbon-carbon bonds in the fuel. I don't have much time left, so I will probably skip this study, which is a dual fuel study of different fuels, methanol and OME. I would like to spend a couple of minutes talking about some of the current projects that we have on hydrogen engines. We are currently revising and repurposing one of the optical engines that I introduced before, where we will have a 200 bar hydrogen pack located outside that is reduced to 40 bar before entering the lab. And then using different pressure regulators and a boost pump inside the lab, we will be able to reach up to 700 bar of injection pressure for direct injection hydrogen operation, even if we have the outside hydrogen pack at approximately 3 bar, so that we can empty our hydrogen packs efficiently. We're targeting a stepwise approach with our optical engine, starting with operation on diesel without hydrogen. Then we will move to diesel hydrogen dual fuel, where we have port fuel injection of hydrogen and ignition using a small quantity of hydrogen injection. We will then, of diesel injection. We will then move to port fuel injection spark ignition of hydrogen, where we ignite using a sophisticated spark inside the engine itself. And then gradually we will move from low pressure direct injection of hydrogen towards high pressure direct injection of hydrogen with a late direct injection diffusion flame of hydrogen as shown in the optical combustion vessel. This may be combined with turbulent jet ignition or a so-called pre-chamber assisted spark ignition, which is also topic of the next project. Something that we have to consider when operating an optical engine is that we operate these engines on skip firing. That means that we want to reduce the heat load on the engine by injecting fuel only 1 out of 10 cycles, for instance, or 2 or 3 out of 10 cycles, instead of firing the engine each cycle. That means that EGR, the typical exhaust gas recirculation, becomes impossible because you dilute the exhaust gases by the intake air. And therefore, we simulate exhaust gas recirculation by premixing air, nitrogen, and water using mass flow controllers. Well, we can then still do EGR measurements, but for hydrogen that becomes difficult because normal EGR measurements are based on CO2 formation, and therefore we have installed also wideband oxygen sensors in the intake and the exhaust, and that we then verify in our system where we do run on diesel, and we do use the CO2 formation method to check whether these EGR percentages are correct. Another thing that is, of course, relevant is still to measure these emissions, because I'm mentioning here that we use skip firing, but yeah, because of the fact that you dilute the exhaust gases, you also underestimate the emission measurements. Skip firing further also alters the heat losses because, well, the engine is cooling down further, and you reduce the amount of internal EGR because, well, you have some non-fired cycles there as well. So together with our postdoc Furkan Akbulut, Stan Latten is now also studying the impact of firing percentage on our metal engine, where we can do both full firing studies as well as skip firing studies. And that's very quickly shown here. So here I'm showing the results of 10%, 20%, up to 100% of firing of the engine, looking at the heat release as a function of time. And there you can see that, yeah, the heat release scales with the fired fractions. And we see that at 10% fired, so 1 out of 10 cycle fires, there is a relatively large premixed burn. So that's the case here in purple, this one, because of the fact that there's no internal EGR. So there's less exhaust recirculation inside the engine itself. And therefore, there's a little bit of a higher premixed burn. That also means that the ignition delay is decreased with the firing fraction. But there is the counteraction between, let's say, internal EGR and the lower temperatures because of the fact that the heat load inside the engine is reduced with lower firing percentages. We've also already looked at some of the emissions, and I will quickly go over these, but what we see is that CO emissions, they increase with firing percentage because of the fact that there is less exhaust gas, less oxygen in the exhaust gas. And specifically the NOx emissions, they initially drop and then they increase again with firing percentage. And again, that's linked to the increase in firing percentage and then the increase of internal EGR and temperature, we believe. As a final slide, I would like to introduce a final study that our PhD student Noud Maes is now looking at. He's looking at the use of hydrogen pre-chambers because hydrogen engines are typically operated lean to maximize efficiency and to reduce NOx emissions. And the challenges here are the combustion stability, NOx, and the reduced flame speed of lean burn operation. And one potential solution here is to use a pre-chamber. So in a pre-chamber, we have a hydrogen charge that is injected into a small pre-chamber that is shown schematically here. In this small pre-chamber, you therefore have reliable ignition of your hydrogen, and that then injects reactive jets into the main chamber to ignite the main chamber hydrogen in a more volumetric sense, to increase combustion stability and to increase the flame speed inside the engine itself. We will use our constant volume chamber for this to really characterize the reactive jets and the ignition behavior in different steps. So we can do overflow of the pre-chamber, as well as the use of a second injection system in the main chamber. And then eventually we also target to use our single cylinder research engine to find a balance between the combustion duration and the heat transfer losses in such a system. And the current prototype is shown here on the right-hand side, where we also have pressure sensing equipment inside the pre-chamber itself. All right, so that brings me at the end of my presentation. I realize I overstepped the time to some extent, so I hope that's not too much of a problem. But if there's room for questions, then of course I'd be happy to answer some.
Thank you very much. I think we can take a few questions. I don't know if there is anyone who is interested. You can simply unmute yourself and ask the question. Cyril, thank you. We can't hear you, though. Just a second.
Can you hear me now?
Yeah, yes.
Yeah.
Yeah. Okay, so thank you for the talk. It was really interesting, and it's quite impressive what everything you can do in your lab, and with the experimental part, it's really impressive to see that. I had the first question about the last couple of slides that you show about hydrogen engine. Did you study the impact and the difference between EGR and water injection about the emission? And if that's so, which is the best in terms of emission reduction? And is it interesting to study both of them at the same time or not?
Mm-hmm. Yeah, that's a very good question, in fact. And in the design of our optical engine, what we are targeting is, and that's probably shown here. So we are targeting here a water port fuel injection. And the reason for that is mainly to reduce the in-cylinder temperatures to mitigate NOx emissions. But we haven't actually performed these experiments yet, because this engine is currently being rebuilt and repurposed by our PhD student. And meanwhile, he has been using our single cylinder metal engine. So this is the optical version, to look at the impact of skip firing. Last week, we've installed the hydrogen injectors on that setup. So yeah, we expect the first hydrogen results on a short term, but it is too early to say anything about the water injection thus far. We haven't implemented that yet.
No, it's a really interesting thing, and I don't know if you have any insight on. Will it be really interesting to keep H2O in port fuel injection, or will it be interesting to maybe put that in direct injection, and to see the effect on that? I don't know. And also, I had a question, but will it be interesting if you are using a nitrogen engine in a CHP system? What will be the best? Will be direct injection? Will it be H2O injection or EGR in terms of keep the maximum of heat in the exhaust gas?
Very good questions. I'm not sure if I can actually provide an answer. So in terms of the comparison between port fuel injection and direct injection, the simple answer there is that with the engines that we target, which are still heavy-duty engines, but not of typical marine size, packaging is typically a challenge. Meaning, if we have direct injection of hydrogen, which is of course in terms of volumetric efficiency what we want, right? We do not want to displace the intake air with the hydrogen that we're injecting, because the amount of the volume of hydrogen that you have to inject is relatively high, right? So you want to inject directly in order to increase the power density of the engine. With packaging restrictions, that means that I think the most sensible way of introducing water would be in the intake, because, well, water at least you would initially introduce in a liquid phase, and you're not that concerned with the displacement of air to that extent, while the latent heat will help you reduce the temperature nevertheless. So I think, yeah, it's a fair question, but of course, direct injection is more complicated because you need higher pressures, and the packaging may be more complicated in order to get everything, yeah, inside the combustion chamber, right? So you need hydrogen, an ignition source potentially, and then additionally another injector for water, perhaps. And then your second question was about the combination in a combined heat and power setup. Well, and your question was more related to
about keeping the heat in the exhaust gas, but in the same time cooling down the combustion chamber in order to reduce the NOx. And then my question was, what will be the most interesting to study? Will it be keeping the EGR, and like you said, depending on the load condition and the rotational speed, changing the EGR, or in the case of hydrogen engine study, would it be more interesting with the water injection?
Yeah, again, that's a very good question, and the answer is that, well, it's complicated. It is complicated. So, well, it depends also on let's say the dimensions of your system, right? So for combined heat and power, well, yeah, it depends on how you extract that heat. So in the study that we did, there was also a flue gas boiler that was more used for the, let's say, the heat production. It was not so much from the engine exhaust that we were using the heat potential. And in terms of EGR versus water, well, I guess for EGR, you also there's more of a, yeah, EGR of course helps with the change in the yeah, it may have more of an impact on the ratio of specific heats, but I'm not sure. We have to evaluate that. Yeah, but you lose in any case the additional cooling capacity because of the latent heat of the water injection. So that that is a big difference. Yeah.
Okay, thank you. I don't know if I still have room for one small question.
Go ahead.
But it's really a small one about the first study on the CHP that you mentioned. You mentioned that you did the 500 hours running. I guess you were running on the same operational condition.
Yeah, correct.
And in order to, for example, dynamically respond to a heat or an electricity demand, would you consider to change those operational parameters? And would it be really interesting to sometimes sacrifice some electrical efficiency in order to have more heat efficiency?
Yeah. Well, again, so the heat and the power are separated in this system, right? So the heat is mainly coming from this flue gas boiler. So that's shown here. So essentially, a lot of the heat component is coming from this part of the system, while the engine is mostly for the power production. But so the answer is yes. I mean, we tested the engine at different operating points here as well, so different loads. That is not necessarily an issue, like it isn't with a typical diesel engine at the moment, right? Of course, it has its optimal running point, meaning that, well, depending on the load of the engine, you will get a higher efficiency. So yeah, the best thing is to indeed, if you have a specific typical power output, to couple an engine operating at its sweet spot to that load, right?
Yeah.
So yeah.
Yeah. Okay. Thank you.
But it is possible to run the engine at different loads, of course. Yeah, and
Yeah,
that's
yeah,
also
yeah.
what we've done. Yeah.
Okay. Thanks a lot. It was really interesting.
Yeah.
Thank you, Zvi, for the questions. I think it's always nice to have questions for our speakers at the end.
For sure.
Okay, I don't know if there are other questions. In that case, I would really would like to thank you very much. It was very insightful. I'm very impressed by the powerful things that you can do in your lab. So thanks again.
Yeah, thank you for the invitation.
Thank you everyone for attending, and see you the next time. Thank you.
Thanks. Bye.
Bye.